All right, the last type of graph we're going to do in this unit isn't exactly a rational function. Well, I shouldn't say isn't a rational function, but they do exhibit EBAs. So it's important to just notice that there are, and as we've already seen before, there are different types of functions that still, even though they're not a polynomial over a polynomial or can't be written as such, they still have some end behavior asymptotes which can help guide our graph. So let's look at 1a and b here. So how can I simplify what the square root of x squared is? The temptation is to say x, but it can't just be x, because remember, because it is x squared, I can put, the domain here would be all real numbers. So there could be negative values for x or positive. But the problem is, coming out of a square root, you can't have negative values. So the square root of x squared, again, has to come out as a positive. So we have to say that this equals the absolute value of x. Okay, and so the domain here, as we just said with everything, and the range, because we're coming out of a square root, would just be 0 to infinity. And the absolute value graph, if you remember from the first semester, just looks like that. Well, let's do the same here for b of x. Instead of just having x squared, this time it's x minus 4 squared and the square root of that. And it too will come out as the absolute value of x minus 4. Domain, still all reals, range 0 to infinity. And so this looks very similar to 1a, except it's going to be shifted to the right 4 at 4, 0. That's its lowest value. Again, but similar look. Okay, so why can this help us? Well, if we have something under a square root, and we happen to have something squared under a square root, let's think about as x, remember an EBA is all about what happens as x gets huge, positively and negatively. And that's going to help guide our EBA for these graphs. So first, before getting there, let's see, it's first asking to find the domain and range. Well, the domain here is there's no restriction on what I can put in for x. But for the range, if the smallest x squared can be is 0, then the smallest this whole quantity can be is the square root of 9. So the range will be 3 to infinity. Are there any x-intercepts? Well, no, because 0 isn't even part of the range. But we can find the y-intercept. So the y-intercept, when I plug in 0 for x, I get 3 for y, so I have a y-intercept of 0, 3. Now the EBA. So if I think of it as x gets huge, well, what becomes less relevant? Well, the plus 9 in this case becomes less relevant as x gets huge. So I can then think of my EBA as being the square root of x squared, which we just learned from number 1 is the absolute value of x. So my EBA in this case is going to be y equals the absolute value of x. And so at the ends, the graph should be getting closer and closer to that. So let's take a look at what we have here. So we have this y-intercept of 0, 3. I also know that's my lowest point here. And then I've got the EBA of the absolute value of x, y equals absolute value of x. So my graph will take on a look like this, getting closer and closer to that EBA. All right, let's do the same for b of x. And instead of our EBA here being absolute value of x, as x gets huge, it's really that x plus 1 squared that is going to be dominant. So my EBA is going to be the square root of x plus 1 squared, which, like we saw in 1b, is going to be something, in this case, it'll be y equals absolute value of x plus 1. That's my EBA. And my domain, let's go back to the domain range. My domain is everything. My range, well, the smallest this function will be when x is -1, making that quantity squared 0. So the smallest will be square root of 4 or 2, which tells me there's going to be no y-intercepts here. The y value is b of x can never be 0, so there's no x-intercepts. Did I say x-intercepts before? I meant to say there's no x-intercepts. But there is a y-intercept, and the y-intercept is when you put in 0 for x. So the y-intercept, when I put in 0 for x, I'm going to get the square root of 5. So 0 square root of 5 is my y-intercept. All right, so let's graph this. So my lowest point, remember I said, is when the quantity x plus 1 is squared, it equals 0. And so that's going to be at -1. So the lowest point is -1, 2. I've got my EBA of x plus 1. So it's going to be that absolute value graph shifted to the left. And then my y-intercept is root 5, so a little bit more than 2. And so this, again, is going to take on the same look as the one to the graph to the left. It's just been shifted over. Okay, so let's do something. Let's just do a couple more. And so you're going to find that, right, in these two problems that I did, when I had something squared plus a value, notice that my graph was always above the EBA. Well, that's not always going to be the case. So let's look at when it is not above the EBA. So let's do C of x here. So the first thing, let's figure out my domain here. For the domain, I need x squared minus 9 to be greater than or equal to 0. In order to do sign analysis, I'm going to factor this. So thinking about when this is greater than or equal to 0, well, that's going to be at my extremes. So my domain is -∞ to -3 inclusive, union 3 to infinity. And my range, well, it will be, the smallest is when the inside of this square root is 0, and the biggest will be infinity. So the range is 0 to infinity. And now let's do the EBA. So the EBA is, again, as x gets huge, the -9 is becoming much less important. So the EBA is going to be the square root of x squared, or y equals absolute value of x. All right, and then we know I have x-intercepts, right? Because when I did my sign analysis for the domain, it equals 0 at -3 and 3. So that's important. And does it have a y-intercept? No. So because I can't do the square root of a negative. So x-intercepts are plus or minus 3, 0. No y-intercept. All right, so let's see what this graph here looks like. Running out of room a little bit. So maybe I'll draw my EBA first. So the absolute value of x. And then I've got my x-intercepts of 3 and -3. And then as I go, I'm going to eventually go towards my EBA. So that's what a square root graph with a quadratic underneath looks like when it's below the EBA. Let's do one more of these. So in this case, instead of just x squared, I have x plus 1 squared, but it's very similar type of problem. So let's start by finding my domain here, which will also help to figure out if there are any x-intercepts. I need x minus 1 squared minus 4 to be greater than or equal to 0. Which if I figure out, all right, let's figure out where this equals 0. So let's see where this equals 0. So I've got x plus 1 plus or minus 2. So my x-intercepts are -3 and 1. So if I put this on a sign chart, this will help with my domain. So if I put in something greater than 1, like 2, this will be positive, and then negative, positive. Okay, so my domain here, I'll put it up here, is -infinity to -3, union 1 to infinity. And let's talk about what the range is here. Well, the range is the smallest is going to be coming out of square root, can be 0, and in this case it does achieve a value of 0 at the x-intercepts. So the range would be 0 to infinity. All right, and let's see, are there any y-intercepts? No. When I plug in 0 for x, I'm getting a negative under the square root, so no y-intercepts. All right, so now we've got all our, oh, I forgot to say the EBA. The EBA is going to be the square root, it's going to be the square root of x plus 1 squared, yes, but it's equal to the absolute value of x plus 1. All right, so let's do our graph here. So the EBA is shifted to the left one from the other one we did. And I've got x-intercept of 1 and -3. And then it's just going to get closer and closer to the EBA as it goes towards positive and negative infinity. So that's the other types of graphs. So they fall into two categories, the one that's above the EBA and the one that is below this absolute value EBA. Now, the only other added piece, which you will see in the problems below, which I'm noticing are both labeled E of x for some reason, the extra step here is you have to complete the square to put it in a form like D of x or a form like B of x on the previous page. So again, the extra added step is completing the square. So let me just, for E of x, I'll just go through that quickly. So to complete the square, I'm just going to put the 29 over to the side a little bit. Remember, you have the linear coefficient, so half of 10, which is 5, and then you're going to square it. And so that means that is what I'm going to add in order to complete my square. But if I'm adding 25 in order to balance it out, I've got to also subtract 25 here. I don't have an equal sign, so that's why I'm not bringing the 29 over to another side. I'm just rewriting this expression in a different way. So if I'm adding 25 in order to complete the square, I must also subtract 25. All right, well, x squared plus 10x plus 25 is a perfect square as intended. So x plus 5 squared, and then I've got this plus 4. So now this is in a form just like b of x, where you have this quantity squared plus a number. And so then you should be able to draw a graph similar to the one you did in b of x. So that's it in terms of the graphing for this unit. So I want you to finish the two E's, I suppose, and then there's some more practice with the other type of rational functions graph. The ones I've given you are interesting, so definitely try them. This is number 3, 4, and 5.